So we've explored the idea of blood volume and resistance. So now we look at blood viscosity and blood viscosity's effect on blood flow and blood pressure. So we say this is directly related to resistance. In other words, if your blood becomes thicker, per se, and the way it's going to be thicker is there's going to be more cells and less plasma. So currently a normal hematocrit is somewhere around 45% packed cell volume and therefore 55% plasma. Well, if you start increasing the number of red blood cells, then you're going to have a greater viscosity, and it's going to be harder to push that. Conversely, or I should say, or you could look at decreasing the amount of plasma through something like dehydration. But regardless, again, you have a problem because the blood is thicker, there's more stuff in it, so there's more drag, more friction and contact with the wall, and therefore resistance goes up. I said, so increased viscosity, you will decrease flow, right? Since it is directly proportional to resistance, and we know if resistance goes up, flow goes down. We know now that if viscosity goes up, flow goes down, right? This viscosity depends on plasma proteins and formed elements, as I mentioned already, especially the red blood cells. So I mentioned, the effects of polycythemia, anemia, or liver disease on blood viscosity. So this is not going to be, again, a typical or key, a typical player or variable that's going to change, just like I said with blood volume. Vessel length and diameter. Diameter is probably the most likely thing to change. Vessel length, well, this is influenced. One way in which it's influenced is as we add body mass and think about adipose tissue specifically, we're going to increase the amount of blood vessels in that tissue, which means we have more tube length to go to push the blood through. So we say that the length is directly proportional to resistance. So again, if the length of the blood vessel increases, again, think you add mass, then you're going to have more resistance. And we remember again that resistance is inversely related to flow. So if resistance goes up, flow goes down. All right? So, and I mentioned here constant, but an increase in weight will increase vessel length, which means you have to have more effort put into moving blood by the heart. So we increase the workload of the heart through this. The diameter of the blood vessel, which is 2 times the radius, and this changes throughout the body, right? And I said, remember that we classified arterioles and arteries and venules and veins and capillaries based on that diameter. So we know that there's going to be a certain amount of normal increase in resistance, which will decrease flow so that we don't have a lot of pressure by the time we get to a capillary. But I do mention that we will be changing this, and this is the most likely thing to change due to chemicals and neural control. And of course, if we have an increase in the diameter, then we get better flow, and we have better flow because we have less resistance. But if diameter decreases, right, the vessel gets smaller, then we have resistance go up and therefore flow goes down. So typically diameter, again, is inversely proportional. So if diameter increases, resistance decreases. If diameter decreases, resistance increases, right? All right. And I just refresh your memory that arterioles are resistance vessels. They are getting smaller and smaller, and we have the choice, because of that tunica media, to control the diameter here. And this, of course, is influenced by the autonomic nervous system as well as local chemicals, like changes especially in metabolic waste or metabolic needs. And I say that overall, we define resistance as a friction. As I mentioned already, it's kind of this drag, the friction between the blood and the vessel wall. And since arterioles are small, the resistance is highest here, and we see the greatest drop in pressure and velocity, right, speed of flow, which is good for exchange. Again, we want to drop the pressure so that we're pushing out an adequate amount, and we're not, right, stressing the walls of these smaller tubes. And we want to slow down blood flow because, right, we want the opportunity to exchange, right? So again, looking at this idea of the overall velocity compared in pressure and diameter, we kind of get this image of what's happening here throughout the circulatory tree, if you will. All right, we have vessel diameter, decreasing, and then increasing again. And of course, we get this average blood pressure just keep dropping, as we've already seen. We see that blood velocity is going to slow to go with this vessel diameter, so looking very much like this. All right, and then overall, we do want to remember that the cross-sectional area, how much overall tubing we have, is actually greatest in the capillaries. So, all right, we get blood back to the heart through the veins, which have pretty much dropped the pressure, right? If we go back here and we see, yes, pressure is pretty much gone close to zero. So how are we going to return to the heart? It turns out that flow is pretty steady. Very little change here because there's little resistance to, cause flow to keep on decreasing. And one of the reasons is because the lumen's big and it's getting bigger as we move. But getting to the heart still is a problem because, like I said, we don't have that push we had like we did in the arteries, right? And again, there's a good reason we don't have that push. But we do want to maintain normally low pressure in the atria, because if pressure builds up in the atria, and this could happen if blood remained in the heart, then we'd have a push against blood returning. So we'd have a resistance of a different type here in the heart, and it would resist the flow of blood back. And we also have valves and pumps, I put in air quotes, because they're not the pump like the heart, but they are still driven by muscle, and it's changes in muscle contraction relaxation that change pressure surrounding the vessel. So it's an indirect pump, right? So it turns out that the valves, again, help us so that blood doesn't keep falling back, and these are especially prevalent in our lower extremities, our legs. We tend to see these valves anytime we have a vein that's larger than 2 millimeters, because it's just a standard, and that's going to be a real problem because of the width of that vessel. It is the fold, it's a fold in the tunica intima, and it looks very much like the semilunar valves, as you see here in this cartoon. All right, so what happens is here we have a vein between muscles, skeletal muscle in our legs. All right, so when you contract and the muscle shortens, it's pushing against the actual vein, which is going to increase the pressure in here and push the blood up and open this valve while this valve remains closed. Right, and then as soon as we relax, right, and the blood tries to fall back, the valves will close like they did in the heart. So we maintain this kind of pressure gradient because of skeletal muscle in our legs, and call this a skeletal muscle pump, as well as a respiratory. So respiration, when we inhale, we increase the pressure in the abdominal cavity, which pushes blood back to the heart because it's lower in the thoracic cavity. And then when we exhale, this reverses, but again, valves prevent the backflow. All right. So what causes the overall, again, exchange in the capillaries? So we haven't caused, we really didn't look at that idea. We said this is going to happen. Here's a layout. But how did it happen? So here I mentioned again that gases, oxygen, carbon dioxide, right, lipid-soluble things diffuse through the wall. So these will just move on from the blood across the cells that make up the capillaries. Since they're just simple squamous cells, right? Glucose, amino acids, ions, and here's examples, have a facilitated transport, and water moves by osmosis, so it moves towards the higher solutes or more stuff, right? If there's bigger spaces, then larger molecules move, so like in the fenestrated or the sinusoids. But these are not efficient enough molecular movements for the needs of the body. So we call the exchange, and we say that it's driven by bulk flow, right? Which is really filtration and reabsorption. And so what causes this? Well, first and foremost is that blood pressure that we now call hydrostatic pressure, right? So I said it's really the capillary blood pressure. And this force pushes blood out of the capillary. And we do refer to this as this method as filtration. Not diffusion or facilitated diffusion, right, or osmosis, all right? And then osmotic pressure, which is, of course, due to the amount of stuff in the blood or in the interstitial fluids or in the cells, right, is a difference in solute to water concentration. So there's a ratio of so many solutes to so much water. Now, in the blood, we have all those plasma proteins that are really too big to leave in most capillaries. So they always remain behind. And of course, this means that there's a high osmotic pressure normally in your blood. And this opposes hydrostatic pressure because it's pulling or attracting fluid back to the capillaries, back into the capillaries. And we call this reabsorption. All right, so as we look at this, right, water and small molecules leave. This is a nice cartoon to show this idea. So water and small molecules leave the capillary if the hydrostatic pressure is greater than the osmotic, which it tends to be at the arterial end. All right? And it enters the capillary if the osmotic pressure is greater than the hydrostatic, which we tend to see at the venular end. So this kind of walks you through this idea that there's no net movement around the mid-capillary, and that's fine. We've done our delivery, and we need to return things to the capillary. So fluid exits because hydrostatic pressure is greater than osmotic, right? They are equal at this point because what's happening here, of course, is that hydrostatic pressure keeps dropping while osmotic pressure is not going to change because we still have the same albumin, fibrinogen, right, globulins that we had here. So we don't see any change in that. What we see is a change in pressure because, as we understood from the previous slides, as we move along the length, right, we have more resistance and, of course, pressure drops, right? And how fluids move depends on the net filtration pressure, which they demonstrate here. So positive out, negative back in, or reabsorption. All right? So I do have to say, look, we have to consider, what this flow is and what we need. So your needs are going to change. And we have to, your body, your blood vessels really, because your heart's just, it'll increase its force and its push and it can increase the amount leaving, but it's really up to the blood vessels to decide where it goes. So here we look at a physiological state of rest versus mild exercise versus a more stressful exercise, right? And you'll see, wow, a whopping 10-fold increase can go to the skeletal muscle, as you'd expect, because the skeletal muscle is going to be doing the activity and it's going to need a lot of oxygen and glucose fatty acids, right? The heart also, right? And we're going to send more blood because here we're looking at how much is moving over a minute, right? Brain is going to stay pretty constant. We do not need to increase it to the brain in this status, in this physiological state. The integument is going to increase here because of heat and the production of heat due to the exercise. So you're going to have a little bit more blood flow to the integument. Kidneys are actually going to drop, okay, because we need the blood out in circulation. We don't need to be filtering as much at this time. We'll catch up when we rest. And gastrointestinal, less blood flow, right? So, again, you're maintaining filtration, but less blood is being delivered, is what that's saying. Gastrointestinal, again, less blood flow here because at this point, if the nutrients aren't in your body, you can't wait for them to get in, all right? And then other structures, modified too. So these would be, again, cardiac outputs. And we talked about this in class, the change from at rest, you send about the equal to your blood volume. As you increase, because heart rate and stroke volume increase, you would get a tripling and possibly more of that blood. All right? So I think we'll pick this up because we're almost out of time on this video in the next and last video, just to remind you how this all gets accomplished. Because this is a very nice, though kind of busy slide.